Okay, now the recording's going back. I was just the last minute or so of the break there, I was starting to copy this link over. So here on my YouTube channel, go to playlist. Well, one I will point to somewhere over here is in the spring when I taught this class in the spring as well, whenever all that stuff happened and all of a sudden everything had to move virtual. So I pre-recorded all the lectures for that. That's what that playlist there is about. But those were the ones made in a hurry. So I might have said things differently there than I will this semester. So those slight differences might, you might understand it better that way. But there's all those videos relate to the same course. Oh, this playlist is what I was looking for. So getting ready for the fall, some of the questions that I've heard before repeatedly, I went through and made some videos kind of answering those questions or things you might have, like talking about particularly what is a logic gate. So that's like a video where I'm talking about logic gates actually flipping switches, not just saying they're switches, and like how transistors work and MOSFETs and a few other things. Registers, you know, that's a word that for a lot of us in class, that's just a word that keeps showing up, and might not actually know what it is, and things like that. So I went through and did a bunch of those. So I'm gonna copy that list and put that on the link in Ivy Learn. I'll put it on the video lectures if you want to check out some of those. There's my edit button. Oh, behind pictures. So those are the way, and then I can hit edit. And it's going really, really slow. There it is. So yeah, it's just a YouTube playlist that has short descriptions on a lot of common components, maybe digs a little deeper into things that are just gonna be like words that might show up in these lectures, but never, without getting a very detailed description about what they are, things like that. It started with questions that I've heard before. I put that playlist together, so I figured I'd go ahead and include it there. So the next thing to look at as far as review, just general concepts before we jump into this, is how computers do math. And have you all seen this before in the SDEV 120 class?
I don't think so.
Okay, so it's just how we represent numbers, numerical representation. I'll put that label up here. Numerical representation.
Do you mean the ASCII characters and stuff?
Yes, that would be one of them. Just how we represent numbers. So we'll kind of go through this as a review just to make sure you don't necessarily forget about it. Hope you may have heard it before. This first part you've heard before. What's a good number? 3,841. Like, how do we know what that number means? So we'll start with our regular, just the normal numbers for humans, which we have 10 fingers, right? Or most of us have 10 fingers. Some people have extra ones. Some people might have lost a finger. But in general, we can say a human has 10 fingers. So over the eons, that became the best number to represent for humans to work with, because then we can represent numbers with our fingers. Then when we started writing stuff down, we invented these digits, but we still wanted our math based off the same thing we were doing with our fingers. So we use what's called base 10, which just means our number symbols are based off 10 digits. The digits 0 through 9. And we line things up in columns, and then each column has a different meaning. So our furthest to the right column, the smallest one, that's going to be 10 to the 0 power. So our base raised to the 0 power, because there's a rule in math that any number we have, if we raise it to the 0 power, that means 1. So 10 to the 0 power, the base raised to the 0 power means a 1 column. And then we just increase the power of 10. So our next column is like 10 to the first power. Then 10 squared and 10 cubed, and it can continue on. 10 to the 4th, 5th, 6th. We just walk up with powers of 10. And that's how we know what those symbols mean. Because we have 3 10 cubes. So 3 times 10 cubed, plus we have 8 10 squared. 8 times 10 squared, plus we have 4 10s and 1 1. Times 10 to the first power, plus 1 times 10 to the 0 power. So to actually get what that number means, we just add all these up, right? 3 10 cubed is 1,000. So we have 3 1,000s plus 8 times 10 squared. So 8 100ths plus 4 times 10 plus 1 times 1. You may not have seen that in a while, but that's how we determine what numbers mean when we just write them out in our daily life, right? You may not have seen that since elementary school, long time ago, because we don't necessarily spell it out every time. But there's nothing special about 10. Well, the only thing special about 10 is humans have 10 fingers. So it's a good number for humans to work with. We can do that with any base we want. Before we get to the one we're actually going to, I'm just going to make up another one here. If we wanted to, we could do that with base 6. So how many symbols would we have in base 6?
6 digits.
Mm-hmm. Yeah, 0 through 6, right? We don't need any extra ones, so we can just use our first few digits. So we actually have 7 symbols. Oh, yeah.
Is
0 through 5. Sorry. The downside of doing it off the top of my head. So in base 6, we have 0 through 5, our first 6 symbols. And we can represent any number by setting up the columns the same way. Our smallest one is going to be the base to the 0 power, which is just a 1. And then we'll have a 6 column, a 6 squared column, and a 6 cubed column. And then we can just kind of put in some digits there. So 2, 4, 3, 5. And then we can find meaning from it the same way as we did here. So we have 2 times 6 cubed. To translate this 2, 4, 3, 5 in base 6 into base 10s, the ones we actually know, we can just follow that same pattern. Plus we have 4 squareds plus 3 6s plus 5 times 6 to the 0, which becomes what? 2 times, what is 6 cubed? I don't know that off the top of my head. 36 times 6 is 6 plus 3, 216. Just quickly writing that out. So we have 2 216s plus 4 times 36 plus 3 6s plus 5 times 1. So that's 5. 3 times 6 is 18. 4 times 36 is 120 plus 24, 144. And 2 216s is 432. So what is that? 432 plus, so 576. 576 plus 28. 604 plus 28, 632, 637. So that's the same thing as writing 637 in base 10. Kind of something we've seen before, right? We've probably never really stopped and worked in base 6, but the key point there is, do you see how that follows the same pattern? Anything we did in our base 10 pattern, the numbers we're familiar with, we can use any base we want and just set up in columns. And when we add and subtract and carry bits over to other columns or borrow from another column, all of those rules still apply. Those rules are independent of the symbols we're using. Does that make sense?
Yeah. Mm-hmm.
So that's what, now that leads into the part we'll actually need here. Is it okay if I erase this?
Yep, go ahead.
I did fill up the board kind of quick there. So that's the pattern. And I'll skip adding them, but we would still, like we learned back in elementary school, when we add and subtract, line them up in columns, just go down the column, kind of like I did here with the base 10 thing. But those rules still apply no matter what base we're working in. One that doesn't show up much in base 10, a rule that probably didn't show up in base much when you were learning base 10, is we are restricted to how many times we can add numbers together. You know, when we line them up in columns to do the adding, like 23 plus 47, we don't want to add more than our base. So in base 10, we would, after, if we had 12 numbers to add up, we would want to do the first 10, then get the result of that, and then do the next one. Because otherwise, we might end up having to carry more than one column over. Right? So like 3 plus 7 gives 0, and we carry a 1. Carrying over to the next column is no problem. But we don't want to carry 3 or 4 columns over. We'd lose track of things pretty quickly that way, right? So we're restricted. We don't want to add more at one time than we have columns. Same thing if we did the multiplying. If you remember multiplying on paper, we'd do our columns, and then we'd end up with some stuff here and some stuff here over offset from it, and then add up those columns. We wouldn't want to do more than 10 at a time. Otherwise, it would throw us off. Not a big deal with 10, right? Because we probably don't even want to add 10 numbers at a time. Even if we had 10 numbers, we'd probably still break that down into smaller chunks to keep track of it. 6, having 6 numbers to add together, that's kind of pushing it. We'd want, if we were in base 6, like was just right there, we'd want to be careful with that. But with computers, we're working in binary, right? Base 2. So that restriction does become a big deal here. We never want to add together more than two numbers at a time, because we risk having to carry several columns over. And then we end up with a mess, because we might end up with multiple things carried to the same column. Let me write that out. We can do that here, but if we were adding stuff together, we might have to carry over too far. And then when we add them up, it's getting the to keep track of because we're not just working here to Mac work. We might have to carry things through on over. So if doing it on paper, you want to make sure and do only 2 numbers in the time. But here in a second, we're going to go over how to do a calculator too. Reviewing it first. Like I said a moment ago, we can choose any base we want. We can use 2 as a base and set up our columns the same way: 2 to the 0, 2 to the first power, 2 cubed, 2 to the 4th. I'll stop there. The numbers get really long really quick. But if we're in base 2, how many symbols do we have? Two, right?
Yeah.
Yeah, we just have the 0 and 1. Which actually makes it a little bit easier. You can either have the number in the column, so to get this value in some meaningful for us as humans, we would just add those up, right? We have 1 times 2 to the 4th plus 1 times 2 cubed plus 0 times 2 to the first. Whoops. Be the 0, 1, 2, 3. Somehow I skipped right into the column, just going on 2 to the 0 power, 2 to the first, 2 squared, 2 cubed. 1 or 0. So really, when we do this part, we can abbreviate that to we either have the number or we don't. 1, 2, cubed, we just say we have it. 0 and 2, we don't have any 2s, then we have a 1. That's how we get the value of that number. We get back to 13. Familiar?
Yeah.
Familiar? Everybody's required to take that course one day. And then we can do add those numbers. There's 0, 1, 1, 4 is 0, 1, 0, 0. And then the thing we did in
I'm sorry, I think I might be cutting out or you're cutting out. Just
is it cutting out?
I don't know if it's
Can you hear me now?
for you. Yeah, I can hear you.
Okay. Yeah, downside of virtual stuff. So the message pops up and everything. If you turn it down, yeah. I'm saying that, right? After I'm together, and just go calm back off. Almost zero is easy. Almost, you know that one, right?
Yeah, you're still cutting out for me.
Let me check my signal. My signal seems to be okay at this moment. Can you hear me now, Jerry?
I can, but it sounds a little bit robotic, so I'm not sure it might be me.
Oh, yeah, this is doing the same thing now. If we give it a second, hopefully it'll come back in. This is stuff we've seen before, right?
Yeah.
All the number representations. We have to do a little bit more in order to actually get the machine to do that, because there's some problems with this. Right. Does the signal keep getting better?
No, not for me.
Well, that can be a little awkward, a little inconvenient. So, yeah, I don't know if there's much I can do. I think it's on the end. All these videos are recorded though, so hopefully it'll come back on here shortly. But to do that, these notes over here. To do math like this, we have to define all our operations separately. Define all operations separately, which can be a bit of a problem. Right? That would make a whole lot of rules that we would have to put together to say what addition is, what subtraction is. Multiplication, division, we can just repeat those. A lot of rules. And we end up with a very complicated subtraction. Here's a little, the picture I'm saying lit up like you were saying here.
I don't know. I may have to watch the recording, but I'll stay here.
So it's being recorded, so what are we? It should be about 20 minutes into the second part of the recording. So to do the math, we have to define all these operations separately, which would be too complicated. What we make a lot easier is if we could do it all in one operation. To do it all with one operation. I'm going to erase this part, if that's okay. This part should be reviewed. Everybody's seen this before. But we'd have to do at least addition and subtraction. And then those two we could repeat. We could just repeat those for multiplication and division. It'd be nice to condense that into one operation. Which in our math classes, somewhere in a math class along the way, you probably saw how we do that with just one operation. Instead of addition and subtraction separately, we have addition, but subtraction really means add the negative. So instead of just working with all positive numbers, just our counting numbers, we want to extend our number line. So instead of going from 0 and heading up to infinity, we want to extend the number line to include negative numbers as well. And then we really only have one operation instead of add and subtract separate, subtract just becomes to add the negative number. So we needed a way to do that in binary. And doing that in binary, well, in base 10, we just add a symbol in, right? If we wanted 7 and subtract 4, we just add the negative symbol in. So our first instinct in binary might be to try and do that. Just add a symbol in, which would be another one of our symbols. We can just add another bit at the beginning and set it up that way. See if that works. So we'll say like 1 for positive and a 0 for a negative, which we defined ourselves. So we could switch that and define it the other way, but I just kind of picked one there for the example. So then if we had a 7 plus negative 4, well, 7's positive, so we just write the binary representation of 7 and add a 1 at the beginning to say it's positive. 4 is negative, so we write the binary representation of 4 and then put a 0 at the beginning and say it's negative. But then when we go through our columns, we couldn't just do the same operation as if we were adding. Because if we're adding, we're going to get right back to this. And then 1 plus 0 would be a 1. So the result of doing that would say a positive 11, but that's not what 7 plus negative 4 would give us. So we actually have to go a little bit further and define a specific negative. So I need to erase this and make room for what computers actually do how we actually get the computer to do math. I'll wait just a second, make sure, since the audio seems to be cutting out. Does it come back in yet? Can you hear me now?
Yeah, I can hear you now.
Okay. Yeah, so just throwing the symbol on the front isn't quite enough. We need to actually come up with another way to represent negative numbers. So that's what we need in order to do math. We need another way to represent negative. And we can do that by using 2's complement. So there's different meanings for this word, not complement like saying something nice, a complement like the rest of them. So if we had sets of numbers, let's say A maybe has the numbers 1, 2, and 3 in it, and set B has, I don't know, 3, 4, 5, and a 6 out here that's not included in everything. We also have the complement of A, which means everything that's not in A. So A has 1, 2, and 3. So what's not in A would be 4, 5, and 6. So complement as far as what's not in them, which becomes super easy in binary because we only have 2 symbols. So we only have 2 symbols, so the complement has to mean the other one. And then this gives us a way that we can use one operation to do all our math. You should have seen the 2's complement in SDEV 120. So just a quick review here on what this means. If you have further questions, let me know. We can go over it in more detail. This is just kind of a review section on how machines process. So, well, let's do those examples that we had. 7 minus 4 is what we want to do. So the first thing we have to do is switch that to binary. So 7 in binary, and I'm choosing 4-bit numbers because these patterns continue. So if we had 64-bit numbers, we would just do this same pattern. But it takes a lot to write a binary number on the board. So to speed things up, I was going with 4-bit numbers. To convert that to binary, 7, we don't have any 8s. 4 will fit in there, which leaves us 3. The next column would be a 2. We still have 1 left, so finish that out. Then to put 4 in binary, in 4 bits, the 2 cubed would be 8. We don't have any of those. 2 squared is 4. Well, we were looking for 4, so we don't have anything left. And then we want to take the complement of that, of the one we're subtracting. So 7 is still a positive number here. We're doing 7, yes, I should really write this, plus -4. So 7 is still a positive number. It just copies over. And then we complement our negative number. So all the zeros become 1s and 1s become 0s. So 0, 1, 0, 0 becomes 1, 0, 1, 1. And then to get to 2's complement, we add 1 to the complement. So we take the complement and then add 1 to get to 2's complement. So 1 plus 1 would be 2, which in binary is 1, 0. So we need a 0 and carry a 1 to the next column. Again, 1 plus 1 is 2. So 0 carry the 1. Have a 1 there and then a 1 there. So that's what a -4 will look like in 2's complement. So our 7 is still a positive number, 0, 1, 1, 1, so the binary representation of 7. And then -4 in 2's complement will be 1, 1, 0, 0. And now we can do our same operation, just that add operation, to get the result of those. So 1 plus 0 would be 1. 1 plus 0 is a 1. 1 plus 1 is a 0. We carry a 1. 1 plus 1 is a 0. And there's this extra 1 over here, which seems like a problem when we're writing it out, right? We started with, add those bits together, and then we ended up with a 5th one. But for this representation, we only have the number of bits we're working with. So for these, we only have 4 bits. So when we do this in 2's complement, we always have an extra bit, which in a circuit, the last wire in the chain just flows back to ground. So it's just, we just discard that last bit. Just throw it away. As far as electronic pieces, when we put the circuits together to do this, there's a whole chain of circuits that are the same for every column. And then we know there's going to be an extra one, so the very last chain just feeds back to ground and throws that last bit away. Then we're left with 0, 0, 1, 1. What is that in base 10?
3.
Yep. So is that the right answer? So 7 minus 4 should be a 3, right?
Mm-hmm.
So that's how computers actually perform the math. Well, computers just carry out this pattern. Whenever we're subtracting, it switches it. It takes the complement of it, then adds 1 to that complement, and then feeds that into the piece that adds column by column, where 1 plus 0 is 1. And 1 plus 1 is 0 with a 1 carried over to the next column. And 0 plus 0 is 0. It just carries out this pattern. And then humans came along and used that pattern as a symbol. We said, this means this. But that's how we do math. If we add, we just take the 2 binary numbers and add them together. And if we want to subtract, we take the 2's complement of the negative one and then add them together. And that way we can do it all with one circuit. And it's actually a very simple circuit that goes together to do that. So that's an important one to know because the regular binary representation, we'll often use that for positive numbers. And if we need a negative number, we do that. And then to get multiplication and division and modulus, multiply, we just add repeatedly. And for division and modulus, we just subtract repeatedly. So and computers have no trouble doing that over and over and over and over again. That's how we build up and can actually do math. So we can perform calculations. But that's not the only type of data we have, right? What time is it? 7:53. So that takes care of our numerical data. But up here on the board, I have the other type of data up here on the board all over the place, right? I just wrote down these symbols, which is kind of messy writing. There's something readable here. Those look more legible. I just wrote down those symbols, and you all looked at those symbols and know that that means that spells out the word better, right? The written language. The way humans have recorded data since that definitive line between history and prehistory. That's where we say history started, is when written language was invented. So we need a way to represent our written language as well, right? Not just our numerical data. And we kind of have that with the binary representation in numbers. Whoops, I forgot to ask. Is it okay if I erase that?
Yep.
It'll be on the video. We can get back to it. Sorry, I always try to ask before I erase the board. But our other main type of data, one that holds a lot more meaning to humans, is going to be written language, right? I'll put the label here. Written language data. Because that's how we, as humans, that's how we really want our data stored. We don't want to know the result of an equation unless it has some meaning applied to it. Right? All right, 12, that doesn't mean much, right? But if I was to add some other things in there, some units, inches. If we say 12 inches, now it means something. We could say that means 1 foot. What's another one that 12 would work for? O'clock. When we add meaning to that number, or that number didn't mean anything until we added the units. So our written language is probably a little more important for us to store. And as programmers, this is one we will actually work with a lot more often. Some people might work with binary. It's important to remember the machines are there, work with that. And at this point, it's hard to predict what you all are going to do off in the future, right? Some people will see binary every day, and some of y'all will never see it again after you graduate or after you finish your classes. Yeah, there's one other spot this semester where it's going to show up very, very quickly when we're doing code, and it'll be a rather minor point. So we won't really see it again this semester. Like that quick review was it. You know, some people see it a lot, some people don't. So in the classroom, we have to kind of review it and make sure you're familiar with it. Oh, one more thing, I almost skipped over an important one. I'm not quite to written language yet. The written language is where we're going to finish up because that's one we're going to work with a lot. But we just looked at, well, base 10. That's how we usually do our numbers, right? Sorry, I almost forgot one of the most important ones. In computers, work in base 2. Humans don't do so well with base 2, right? It's a lot of symbols. If we wanted the anything decent size, so like 134, we would need eight bits to represent that number. 134, so 2 to the 7th, we'd have 128. Minus 128 leaves us 6 bits to account for. So no 64s, no 32s, no 16s, no 8s, a 4, a 2, and no 1s. So we need a lot of bits to represent our numbers. It gets really hard to work with for us. So we need a way to go between those systems. Because going directly between them, it's kind of a mess. We have to do all that math, right? If we have some big long binary number and we want to get to base 10 to make sense of it, 1, 2, 3, 4, 5, 6. We have 2 to the 5th plus no 2 fourths plus 2 cubed plus 2 squared plus 2 to the 0. That is what, 32 plus 16, 32 plus 8 plus 4 plus 1. 45. But we have to go through a whole bunch of math to get there. So, and same thing, if we want to put a number, if we have a base 10, a decimal number, and want to convert that to a base 2, a binary number, we have to do all that math kind of manually because 2 and 10 aren't very connected numbers. And the problem we have with working with base 2 is there's not enough symbols. We need more symbols. Our mind can handle a lot more than 2 symbols, and then we can work with shorter representations of our numbers. So if we need to find a better thing, a better base that works really nice with base 10 and base 2 in order to get back and forth between them and actually work in. So for that, we really just have to kind of start checking numbers, right? And one requirement is it has to be directly relatable to base 2. So if we just start with a 2 and square it, it'd give us 4. 4 has more symbols, so we could, a few more symbols, so representing a number wouldn't get quite so large, but not very many symbols. We can work with a lot more than 4 symbols, right? So the next thing that would relate that good to base 2 would be the 2 squared squared, which would be 16. That might be a good number for humans to work with, right? Because, well, it's got a lot more symbols than base 2, so we don't end up with that big long string that our eyes go blurry trying to read through it because there's not enough information being conveyed in it. It's bigger than 10, but not much bigger than 10. So that turns out to be the best way to get between them. If we need to convert between our systems, we can use base 16, and that makes conversions a whole lot easier. Have you all seen conversions with base 10?
To base 16.
Yes, sorry, base 16, hexadecimal.
Yeah.
Yeah, it makes our conversions much easier. Because then we can pick a number. I'll do 147. Just made up a completely random number in base 10. And if we want to go to base 16, we would divide by 16. So 16 will go into that, what is it? 10 would be 160, so it's got to be 9 times, minus 144 with a remainder of 3. So in base 6, 147 in base 16 would be 9, 3 in base 16. And then to get from base 16 or hexadecimal into binary, we just take each one of our digits, split it up, and do the 4-bit representation of that digit. So a 9, what is a 9 in binary? Do you know this one?
No.
So we have 4 bits. Our smallest one's 2 to the 0, so that's a 1 column, right? The next one is 2 to the first power, so 2 column. 2 squared, 4, and 2 cubed, be 8. So we just need to add those up until we get to 9. So an 8 will fit, right?
Yep.
So I have one of those. 8 plus 4 is 12, so that would be too big. So we don't need any of those. 8 plus 2 would still be bigger than 9. We don't need any of those. And 8 plus 1, that'll give us a 9. So we can just do it that way. So 4 bits is going to be 8, 4, 2, and 1. And just add them back up until you get to that. This is the way you're probably going to want to do the conversions. And then on the other half, we need 4 bits to represent 3. So how do we represent 3 in binary? I think it was on the board a moment ago.
0011.
Yep. So we take each one of our bits separately, write out that, and then those together is the 1-byte representation of that. That make sense?
Yeah.
So whatever decimal number we had, and this should still be reviewed, we divide by 16, we'll have some sort of quotient and a remainder. And then each one of those, that's our hex representation. We'll take each one separately, find the binary of that, because that'll just be a 4-bit binary. We can find those really quick. Find the 4-bit binary and then put them back together into whatever, and that'll be our actual binary number. So it makes going between decimal and binary a lot quicker. And the other way as well, if we had some binary number, we can get back to base 10 quicker by going through base 16, because humans can handle more than just 1 and 0, right? So we just split it in half and get the hex from each half. 0, 1, 1, 0 is what number?
6.
Yep. So, and then over here, the same thing. So we're back. We start over as a 4-bit number. So we have 1, 1. Well, I like to start on the big side, and then that way the numbers get smaller as we add them up. So our big side's 8. We have 8 plus 0 is still 8, plus 2 is 10, plus 1 more gives us 11. And, well, 11 is more than our digits, right? So what symbols do we use if we have 16 numbers? Obviously, we're going to use our digits first, right? But then we need a couple more symbols. 0 through 9 is 10 digits, but we need 16 if we're working at base 16 or hexadecimal. So we still need 6 more symbols, and we just use A through F. So we have 11, and this we can just count on our fingers. All you need to do is remember A is 10. So if A is 10, then B, C, D, E, F. And you can count out the rest of them on one hand. So we need 11. A is 10, so that B would be 11. Whoops. So that number I just made up, our hexadecimal representation of it is going to be B6. And to get back to decimal, then we can do that a lot quicker than all of those. So B is 11, and that is in the 16 to the first column. So 11 times 16 plus 6 times 1. Which is a lot easier to do the math, right? 11 times 16 is how much? 160 plus 16, 176. So 182. And that little bit of math goes a lot quicker than if we did each column by itself, right? Than if we did what do we have? 128 plus 64 plus 32 plus 16 plus 4 plus 2. There's a lot more steps to do it directly. So we use hexadecimals to convert between them. That's the primary use for it. And if you have a binary number, just split it up in chunks of 4 and then find the representation of each 4-digit number. If you have a larger, if you have base 10 and want to get to binary, divide by 16, you have a quotient and remainder, and just each digit in the hexadecimal number, take by itself and find the 4-bit representation of that. Or use a calculator, right? That's pretty easy to do as well. Lately, I've been recommending these to people, just because it came from the Dollar Tree. So a $1 calculator, and we can do all the conversions right there on it. They're above the operations, above the division. It has sends a number to binary. So like this one here, we did 147, and then second, and the thing above the division key gives the binary on that, which is a mode, because now if it's set for binary, I can't enter any numbers except ones and zeros. So if we have a binary number, 0011101, some binary number, and want that in decimal, we just put second, and above the plus sign has the decimal. So you get 77. And there's a hex key or octal key, which is base 8. The calculators make that a whole lot easier. If you have a calculator that has that functionality on it and you're not sure how to use it, let me know. I can show you that. We're IT people, so we should probably be using the technology to do the conversions, but at least want to review it really quickly. And also, anytime we work in hexadecimal, that one is going to show up a lot more. You will see hexadecimal. And you said you're a network person, Jerry. You'll see that in network addresses. It also shows up in colors. Hexadecimal shows up. And really, when we see hexadecimal, we will this semester. This is what we're actually working in. That's why most of us never see binary, because we can work in binary 4 bits at a time. And that's anytime we're working in hex, we're actually working in binary, we're just looking 4 bits at a time. Because the human mind can handle more than the computer. Does all that make sense?
Yep.
Stuff we've seen before.
Mm-hmm.
A lot of review. We just want to make sure we know it, we don't forget it, because it might show up. We have technology that'll do all the conversions and stuff. So the main thing we need to remember is, for like hexadecimal, we don't have enough digits, so we add the letters A through F. And when we work in hex, we are actually working in binary directly on the machine. But we just do it 4 bits at a time. So now that other thing I tried to jump the gun for, the one that we will use quite a bit is our written language. So a term you've probably heard before, our written language, we refer to that as in particular, it's a string of characters. An array of characters. We'll talk about that a little more depth when we get to the section on arrays in a couple of weeks. But a character is a single symbol we put together and build our words in written language or symbols. Traditionally stored data or conveyed information, kind of what's going on in the border there. Writing these words down, we don't know what these letters mean. So obviously we need to work with them a lot in programming. So to represent those, we just set up an encoding scheme. So I guess one way to look at it is we just pick a number and assign each character that we can represent a number. Right? So we would say pick a 65 and call that a capital A. A 66 and call that a capital B. Right? I think we've probably seen these before. Coming down the alphabet, 97, lowercase a. We use count two that on the back. Our digits are in there. 32 is a space. 9 is a passkey. There's a whole lot of them in there, right? And in your SDEV 120 class, they probably mentioned ASCII code. Right? The ASCII code, but ASCII code is not the only one. In particular, the A here stood for American. So ASCII code was kind of only restricted to English, which leaves out a whole lot of symbols of what the humans use, right? So you can also use Unicode. And Unicode is an expansion of ASCII. So all the stuff you learned about ASCII code, that will expand up into Unicode. For working in Python, we'll be using Unicode. So we have access to all those other symbols too, not just the English language symbols. It takes a few more bits to represent it. We represent each number with 16 bits instead of 8. But we can hold almost any symbols humans use. Actually, not quite all of them. We have to jump up one more time to get to every symbol. The one I like to refer to is Egyptian hieroglyphics. If you wanted to write in hieroglyphics, not just insert the pictures, but actually type on the keyboard and have it show hieroglyphic symbols, we have to go up the next step and we have to use a 32-bit encoding, which is still called a Unicode. It just gets a different number on it. But we'll use Unicode 8, which is an expansion of ASCII code. And basically we just take one of our binary numbers and say, that means this symbol. So 65 in base 10, there's no zeros, no 128. We'd have a 64, no 32s, no 16s, not any 8s, no 4s, no 2s, then we have 1. So the binary representation of 65 is how the computer actually keeps track of an 8. And same thing for all of our symbols. Whichever symbol we're working at, we just assign each character a number. And then something that won't matter to us this semester here in Python. Notice over here, when I wrote string, I used double quotation marks. And then when I wrote these, just a single character, I used a single quote mark. So in some programming languages, those are interchangeable. Some programming languages, it doesn't matter if we want to use double quotation marks or single quotation marks. The only restriction is that we have to close the same one we opened with. Right? We can't use a single quote mark, write a bunch of words, and then put a double quote mark at the end. We have to close it with the same one we opened it with. But we could use either single or double. And for us this semester, Python's one of those languages. It doesn't matter which one we use. But depending on where you go after this class, sometimes it does matter. And if it does matter, the single quote marks represent a single character, and the double quotation marks represent a string. You may need that further down the line somewhere. But does all of that make sense? Just the Unicode or ASCII representation, we just pick a number and say that's how we're going to represent an A. And just encode all of our data to that letter. What else do I have on the notes here? Got logical operators on here. I'll talk about those when we're doing an example. There's one more thing I want to talk about for possibly review. You might be somewhat familiar with this. Is y'all okay with this? Is that all right if I erase it?
Yeah, you can.
Most of that should have been reviewed. Just getting us ready so that Wednesday we're ready to jump in and start programming. And then most of the examples, most of this semester will be 2 examples. And what'll get written on the board, some diagrams to help visualize what's going on and represent things. One of those diagrams I wanted to draw here, one that I'm going to use a lot to represent stuff, is called a stack heap diagram. Have y'all ever seen one of these diagrams before?
No.
So it's a way to represent what is going on when we put a program together. So stacks and heaps are what's called data structures. We're not getting into that a whole lot, but the quick version of that, a database is storage and a data structure is memory. It's how we get our data into memory, around memory through all the processing, and then back out of memory. So stacks are like a stack of plates. We feed in an instruction and just stack them up, and then we start with the last one that went in and carry out that instruction. We go to then we go back down the stack, the pile, and carry out those instructions one at a time. Kind of like when we wash dishes and then put the plates away, the last plate we wash will be the very top of the stack, which means it will probably be the first one to be used. The last one to get put on the stack is the first one to get used. And our programs, the code we write in standard programming languages, are processed as a stack. So in these diagrams, the stack side represents our code. And a heap is a dynamically allocated memory, a dynamically allocated structure. So we choose a block, use that, and for the next one, we can choose the next block anywhere in there and just scatter them around, kind of scattered around. Actually, heaps are a little bit beyond the scope of this class, but instead of the nice organized stacking thing, stacking up our instructions, we're scattered all over memory. So really this is RAM. And this is how we'll represent RAM. So we might put a program together that asks the user for a name. And in our code, we're going to have this variable called name. And a variable is simply a named location in memory. Over in RAM somewhere, the computer is going to store that. It's going to set a bunch of bits aside, a bunch of spots to stick bits in there. And I don't know, maybe this one starts at bit 184,213. Well, that's time for the computer to remember where that starts at. But we'll never remember that, right? Even if we only had one piece of data and it was in a good number, we'd never remember that. So we need a way to refer to that. So that's all a variable is. It's like a name spot in memory. One way I like to describe it is it's like an address. Right? If you're talking to people that live in the same neighborhood as you, you wouldn't necessarily have to describe an exact street address to let somebody know what house you're talking about, right? You say the house with the green shutters or the Joneses house over there. And your neighbors are going to know who you're talking about, right? Because you're familiar with it. That's what the computer's doing here. It's familiar with it. And it's going to just, every bit is numbered. So it's going to know where the data is based off the number of that bit. But we're outsiders. Somebody from outside the neighborhood, somebody that lives in Missouri and is coming in to visit or coming in to deliver some a camper they sold on Craigslist or something, they're not going to know what you mean if you say the Jones house, right? Jones's house or the Smith's house. For them, you need to give something more specific so that an outsider can tell, which in the case of a neighborhood would be the address. Be like, oh yeah, over at 2418 Sunny Street or whatever, something an outsider can make sense out of. And that's what a variable is. It's just a human, a reference to that same spot in memory that is more meaningful to a human than a computer. But these diagrams are probably the ones I will use the most to represent things when we start working through examples. And on the stack side, we put things about our code. So like the variables pointing over at some spot in memory. And then over on the heap side, that's how the memory is being allocated. Like here, I put those blocks all together. But there's different ways. Maybe it could be represented by a block there and another block down there with a pointer going between it. Another block up there with a pointer going between it. And then at the end of the piece of data, it just points to empty space. So a way to represent how that data is actually stored in the CPU. Does that make sense?
Yep.
So yeah, that's mostly what's going to go on the board. I think you asked that earlier, Jerry, about what sort of stuff. It's going to be pictures like that, some UML, like use case diagrams, and things to help make sense of what the programs are doing. So we're mostly going to be doing examples of programming. So I guess they'll probably be writing some code on the board too, plans and algorithms, but mostly a lot of pictures to help make sense of stuff. And that's going to be one of the ones I use most often. It's the stack heap diagrams because it shows what it says in our code and what's actually going on in the RAM. The last picture I want to draw here is kind of what computers are doing. Well, we know there's two things there, right, involved in processing. We're going to give it some sort of input. A bunch of stuff happens, and then down at the bottom, we get to some output. And in particular, at this point, I'm thinking about the processing, right? So the broad scope, we just have this big bubble here that the kind of not knowing anything about computers, right? Just the basic. We give input to the computer, a bunch of stuff happens, and we get back output. So we want to be a little bit more detailed than that in the classroom. In particular, the input is somehow going to feed into a CPU. A bunch of stuff, and then go to the output. So there's kind of a flow there. But again, we need to be a little bit more detailed about that in the classroom, right? I believe there's questions about the CPU on the quiz. That's why I wanted to cover this. So just to go through this, like how does that input work its way through to the output? Just the broad picture here. So the first thing is that input gets put in RAM, our volatile storage, the temporary storage. It's only there for when we need it, the working memory. And after that, there is a control unit keeping track of everything. So like this whole big picture, I'm kind of expanding out the CPU here. I guess I almost drew RAM as part of the CPU. The RAM would be a separate chip, but it's they go together. Then the main thing, any more room? The main part of the CPU is going to be a control unit. There's a control unit keeping track of everything. Once those things get, the input gets pushed onto the RAM, and when the control unit's ready, it will pull those values from RAM and push them onto, well, one of two places. Either an arithmetic logic unit or a floating point unit. They basically do the same thing. It's the piece we do math with. I guess I'll write it with a decimal number. Going back to base 10, the numbers we're familiar with, 1,238.7496. When we're working with our integer part, our whole number part, they get bigger that way, right? And corresponding to the fractional part kind of needs to go that way. So those two pieces are the same thing. It's just one works to the right and one works to the left for the whole numbers of the fraction. But whichever one that needs to get pushed onto, the control unit will then push the value into the right one of those. And from there, it will get pulled into some registers. Registers are just holding places. Think of it like a storage place. If we're working, it's the size of the data we're working with at a time. So if we're working with 8 bits at a time, we'll have registers that hold 8 bits so that we can do something with all those bits at once instead of one at a time, like the processing would use. Or the RAM holds them 1 bit at a time. It doesn't know anything about them. So the registers hold them a large chunk at a time. 8 bits at a time, or any more, really 64. There might still be some 32-bit machines that haven't completely failed yet, but pretty much mostly 64 bits anymore. So when we have all 64 bits together, they have some meaning. They do something. So that's what registers are for. And at that point, the control unit can communicate with that, see if that's the final result. If it is, that the contents of that register get pushed to the output. If not, it can push them back onto our arithmetic logic unit or a floating point logic number unit. And that's kind of the flow of the data as we're working with as the CPU works. And one important thing I wanted to note about this picture is input gets pushed onto RAM, and then the control unit pulls things from RAM. RAM itself doesn't do anything. It just sits there. Same thing with the ALU and the SDU. Those are circuits that carry out a particular pattern that will run the bits through, but they don't do anything on their own. They just sit there, and a bunch of bits gets pushed onto them, go run through their pattern, and then on the next pulse of the clock or whatever, the registers are going to pull the values out of that. So a lot of the pieces are just sitting there, and only certain ones actually move them around. I wanted to make note of that, the push and pull, and break that down a little bit more, some of the main components of the CPU. I guess I should, if I'm listing out components of a CPU, I should probably also put clock there, because all those do need synchronized. We don't want to take values from the RAM and put them in the ALU while it's still working on the previous one. So a clock to synchronize everything, and then moves from input into RAM temporary storage. The control unit will ask for it when it's ready. The technical term is going to be fetch. When it's ready, the control unit will fetch those, push them into one of the processing, ALU or FPU, which is kind of the execute, and then on to the registers, which is the technical term is going to be execute there. And either go to the output, or it could go back to RAM. I didn't really draw a circle there. If that data is needed, the control unit can then send it back to RAM as well. But the general flow of a CPU, and a very rough picture there. Hopefully that kind of made sense. The user pushes stuff into RAM, temporary storage. Then when the control unit's ready for it, it fetches it from temporary storage, runs it through executes it through some sort of processing, and then checks to determine if it's done with it or not. Just a very rudimentary picture there. But I wanted to point you all towards another video here, or not a video, a picture. If this is the sort of things that catch your interest, Wikipedia has a really good picture, or has had a really good picture here for several years. That is more detailed than that rough one I just sketched out, but still a whole lot, still simpler than the actual like wiring schematic, the complicated electrical engineering thing. So on the Wikipedia page for CPU, if that sort of thing catches your interest, yeah, this picture here. A slightly more detailed than what I drew on the board there, but the same basic idea, and still a few steps below between, the wiring schematic for one of those right there. And that's an early chip. But that picture kind of makes sense of those. Everybody has interest in different places, right? Some people really like the hardware. Some people really like doing security stuff. Everybody has different interests. So I was just going to point you towards that. This class, so that kind of filled in. That was the whole pack of notes that I had. Yeah, so on the last page of the notes that I had for the review section, I put that is all of that we just talked about. That is the quick version of the how and where, which are, all of that was things you should have heard before in the SDEV 120 class before coming in here. So just a quick review of it. And the rest of the semester is about the why. Like, why is it going to take one of those binary representations of numbers and add it to another? Which is, the short answer to that is we're going to tell it to. So we need to, we're going to tell it to. So why does that need to happen? What are we trying to accomplish? That's what we're going to do most of this class. So most of the rest of the class will be done through examples in Python, and we'll sit here. I'll do a screen share and then talk through an example and why things are happening, putting algorithms together. We'll practice that. So make sure you have Python installed before the next class, Wednesday, and that way you can follow along with the examples and get some stuff done. And I put a video on there for different ways to run Python so that you're not necessarily restricted to working just in the IDE. Like Jerry, you said you're working on a netting degree. So it would probably be better practice for you to run all your scripts in the command prompt along the way. And which degree were you working on, Tom? Oh, don't hear anything from him. He might not be sitting by his computer anymore. But either way, different people are going to have different, might have different needs. So like cybersecurity people as well, it might be better to do that in the command prompt. Do all your scripts in command prompt instead of the IDE that we'll be typing in.
Is there certain features that would be missing from the command prompt in the IDE?
Nope. So we're using a super stripped down IDE. The thing that would be missing from a command prompt is you wouldn't have debugging tools. And the debugging tools in idle are kind of lousy. We will look at them once, and those allow us to do things like step by step. We can run line 1, then go to line 2 and slow it down and run it slower will be the only thing that's missing. So if you run it in command prompt, you will get the same error messages that you will in idle, because we are using the most stripped down type of IDE there is. It barely has any features above what you would do in the command prompt, but actually doing it in the command prompt might be better practice for you. So that's why I put that video together to see how to do that and set that up. But otherwise, we kind of got through very quickly there, went over the background stuff, which should have been review. I think it's chapter 1 in the book. Chapter 1 and 2. Yeah, the book kind of splits it out into those 2 chapters. So then Wednesday, we'll be ready to start writing programs. And what time is it? 8:40. So this is about how long the class is going to last each time. It'll go from about 6 to 8:30 to 8:45, which will leave us, on the schedule it had 9:50, right?
Yeah.
But programming is an active subject, so we need lab time. So the rest of that time on the schedule, we're going to call lab time. We'll finish up the lecture part and sign off Zoom and everything, but I will always be sitting right by my computer. Like, my board is in my gym. It's not in my office. So until 10 o'clock, I will leave my computer in the gym with the good lights on and be ready to ask any questions. So that last hour or so will be lab time every time. But for general expectations, we'll probably be going till about 8:30 every night. Otherwise, I think that was about it for today. Normally on the first day, I like to do introductions, but there should have been a lot more people show up. There was quite a few more on the roster. So I'm going to send everybody an email, and hopefully we'll have more people on Wednesday. So we'll do some introductions with each other then. And Skip is going to stop by Wednesday. So please try to be here right at 6 o'clock So he'll give his little 15 minutes spiel, like he likes to give in all the classes. But otherwise, that was about all I had for this evening. Does either one of y'all have any questions?
Are we going to go over the Python script we're supposed to make for the discussion board?
I was planning on doing that Wednesday.
Okay.
So that will be the first example of what the this was not a typical lecture for this class. So after Skip gives his spiel, I was thinking about doing it. My plan for Wednesday is to do introductions then, since they didn't get done since there was only a couple people here tonight. Quick introductions. I like to hear people's voices at some point, and then we will go over doing that discussion board. We'll kind of walk through it step by step in class.
Okay.
We'll have most of it done.
And then are we going to do a lot more stuff than like print commands in Python, like more stuff above that?
If you want to, we will see quite a bit more.
Okay.
We'll be using Python for the first 6 weeks of the course. And then the last 2 weeks, we'll do something different. And in week 5, one day we're going to look at PowerShell as well. Do all the stuff that we see in Python over the first 5 weeks. We'll see it in PowerShell in like 45 minutes. Because it behaves the same, it's just different syntax. But for the discussion board, we pretty much just need the print command and to store stuff in variables. Do you want to look at some of that tonight, or I was planning on doing that Wednesday, but we can go over stuff right now if you'd like to, Jerry.
Yeah, sure. If you would like to.
Okay, yeah. So kind of a preview of what needs to go in that discussion board. I'm gonna close everything on my computer real quick. Okay, I'm gonna go ahead and share the screen. Have you got idle installed on your computer?
Yeah. Mm-hmm.
Okay, so yeah, if you want to just follow along, we can just start up idle. Whoops, if I can spell it correctly. And idle, as far as an IDE, comes in several parts. So the one that opens here by default, that's our shell. That's where we actually run stuff. So this is like a command line, very similar to command line or prompt, where we're doing things in live time. We can store a number here, store some stuff in variables, do some math. We'll look at doing that later, and print things out right in live time. We can't really save it and reuse it over and over and over again. So to do that, we want to open one of the other parts. If we go to File and New File, we'll get a little text editor where we can type our Python script up as text and save it, and then we can run it over and over and over again. We don't have to just type it in the command line every time. The third part to idle is under debug. If you just go to the debug menu and hit debugger, we have these tools. So if you decide to run it in your command prompt, which would be very good practice for somebody heading into the network program, you wouldn't have these, but it just has some different things where we can pause it along the way and like see the values of all the variables, see the stuff that's running in the background, and get details about what's going on that would, so that we can find problems. Whenever problems happen, we can go through and track them.
How do we, is there a certain command to turn on the debug in the command?
Oh, so there wouldn't be a step through debug. You will still get error messages. So you'll still get the same type of error messages. So for example, I'm gonna do something here. Number equals input, enter a number. And double equals number squared. Oh, I'll call that square. So I'm going to square that number and just print that out. So this does have an error in it. And you will see an error message like this. So we can, instead of typing that over directly line by line, one at a time, and then having to do that again, we can just save this. So you go to File and Save, and I'm just going to save it here in my delete folder. Give it some sort of name, and if you want to type the extension, it's .py. So now those commands are saved. So if I hit run and come up to the menu, run is click this button or just push F5. If you hit F5 on your computer, it'll just go ahead and run. So it's asking for a number, type in a number, and then this error message that popped up, if you run it from the command prompt, you will see that same error message. That comes from the language itself. It's called a traceback. So when something went wrong, it just goes back through the last few steps it ran to see what went wrong. So like in this case, it says something happened on line 2, and then gives the error of what it is. So you will, if you want to run in command prompt, you will see that same error message, which has enough information to fix it. It says on line 2, we can't do exponents between a string and an integer. So we come back over here and look at line 2. Well, 2 is definitely an integer, right? Which means number must have been a string. So we just have to change that input. Whatever input the user gives us, we'll have to change that into an integer. But this is stuff we'll see later. I was just kind of previewing that that error message. So if I save that and run that again, whoops. This time if I enter a number, it'll square that number and print it out. Does that make sense?
Yeah.
So you will receive, and the debugger here isn't a very good debugger compared to some other IDEs that could be used. So mostly, even in idle, we'll be using the tracebacks to fix problems, which you would see those running in the command prompt or command line if you're in Linux. That little video I made went over it in Windows. If you're a Linux user, it should translate almost directly to that. It's just said it, you can check that out. But for that discussion board, we really just need to save some values. And to save values, we will, it's an open type language. We're going to talk about all this soon, so we don't have to say what type it is. We don't have to say we have an integer or we have a string. We can just put a name on it and just say, well, we have a variable. I'm going to leave some white space around. So like the first one, I'll put my name in there. I'll store my name and then my age. And whatever type of data we want to put in there, we can just store in any variable. And we're not restricted. We can change them back and forth. But we do have to be careful about what type it is. Because I couldn't suddenly say, try to do math with this variable. That's what that last error message was. Which I already deleted it now, but it was stuff coming from the keyboard. So Python's going to assume anything coming from the keyboard is a string, because that's where we usually type strings at. So we had to specifically say that was a number. Whatever type of data we have, we can just put it right in a variable. What's another thing? We can store the town I live in. Actually, I think I'm back to exactly what that example I put on there was, wasn't it? And now we can print those out. And to do that, we need to concatenate those together into sentences. So let's say print, and I have my name, so I can just access what's stored in that variable, plus some other words. This is, then I'll access what's stored in age, plus years old. So I just stored a couple data points about me, like we would have in a database, right? we don't store big long sentences or big long essays in a database. We store just little pieces of data, and then we put them together in the output when we're ready to output them. So that's all that really needs to happen on that. Just, save a few data points about yourself, and then concatenate together some outputs. There's actually a problem when I run this one. The same problem. I hit F5. So we get that traceback again, right? Something didn't work right, so it just ran through it just walked back up the last few instructions it tried to run. And the one that didn't work was here on line 8. We can only concatenate strings together. So over here, name is a string, but age is an actual number, right?
Yeah.
Cast things to change the type, we can just wrap that in this little method. So str, that abbreviation for string. So we're going to take that variable and turn it into a string. So that's our notation for doing that. So now if we run that, save it and then run it, it prints out that sentence. So that's what I was looking for that intro discussion board. And also the Python essay will be written that way as well. So you'll save a bunch of data points about the Python language and then concatenate together some outputs to make an essay. But that one's not due till the end of the semester. The book also likes another version of the print method where it's what we call overloading. We can make, when they set up the programming language, they created more than one method called print. This function that we can call. There's more than one of them. And aside from here, we just concatenated together this big long string all at once. Another version of the print one, it's overloaded, so there's different versions we can use, is we can just pass in the pieces we need. So do the same thing, I could pass in what's in the name variable. And then I could pass in the word is. And then I could pass in the age variable. And then I could pass in years old. And write the same sentence. So when I output those, it should look exactly the same. So they F5. See how both sentences look exactly the same?
Yeah.
So it's kind of like there's two ways to concatenate stuff. The book really likes to use this. For the most part, I will avoid it and just do regular concatenation because this only works in the print method. It only works if we're printing to the console, which before long we'll take a look at some graphic user interfaces and we won't be able to use the print statement on those. But the concatenation is what works everywhere. And it's more standard for different languages too. Most of our languages use the plus sign for concatenation. And the ones that use a different symbol, that would be the only difference. Like to do the same thing in Visual Basic, we'd have to use an ampersand instead of the plus sign. Or in PHP, we'd have to use a dot instead of a plus sign. So it just uses a different symbol, but our concatenation would look exactly the same. So I would typically recommend doing it this way, but the textbook, the reference you have right at hand, is going to want to do it use this one a lot. Either one's acceptable. There's more than one way to do things. But does that make sense for what to do on that discussion board?
Yeah. So you want us to do a paragraph of that?
Mm-hmm. Yeah. I can't remember what numbers I put, whatever numbers I put in there. So like so many variables and then just, yeah, enough sentences to make a paragraph about yourself. Only this is a programming class. So instead of typing it up in the text editor, I want you to write a program that introduces you. So also like I did, you can just refer to yourself in third person. So like every sentence can just say Jerry. You don't have to say I or me don't worry about other pronouns. That'll be fine. That way you can just store the name once and then put in some other things about yourself. But again, hopefully there'll be 4 people here Wednesday night, so I will go over that in a little more detail. But the main things of working with Python, so aside from idle, we also have the Python editor. I'll look at that real quick while we're on here. It would just type in Python, or it should be installed in the same folder. You'll get this shell where it actually runs. So the command prompt would be more like this. Notice we don't have any buttons. We don't have any main menu or anything like that. So we can just do our stuff directly. We can put things in variables, so like name, like first name, put my name in there, last name, I'll put my last name in there, and full name. I can concatenate those together. The first name's already stored, so instead of retyping it, I can just refer to where it's stored, plus a space in between them, plus whatever's stored in last name. Does that make sense?
Yeah.
And then it's a way to refer to where that data is stored in memory. And then you can just, if you just type it in, so like if I type first name, it outputs what is stored in that value. So we can build strings up that way, or we can put numbers in there. Num1 equals some big number, and num2 equals, I don't know, another big number. The product is going to be num1 times num2. And if you want just something to mess around with to get started, kind of get used to it, maybe do some of this practice for between now and Wednesday. Just use it as a calculator. Store a number in one of the things, and then store another number, and then do a quick calculation with it.
And then in the command prompts, how do you like erase some of the stuff and like kind of like start over, or like kind of edit the lines before that? Do you have to like restart the command prompt?
You have to redo them again. So you have to go up. So maybe I meant to put Christopher instead of there. So typing it right in here, I can hit up and get back to it, but I really have to redo the line because it's not saved as like a prompt. It's doing it in live time. It runs that command and then it's finished with it. Mm-hmm. So that's what's in that video that I put together. It has a way to store the scripts, use just any text editor to save the script, and then you could run it in the regular command prompt.
So in the command prompt, though, to change something a line before that, you just have to put a different, like a string in for that variable, just like you did there.
Yeah, you can scroll back up, but it's you're working in live time. As soon as you run a line, it's done with it. So that's why it's nice to put all of the program instructions into a script, a file that saves all of them, and then if there's some problem, you can just go back in and edit it.
Okay.
Or did you mean like change it all together?
Yeah, if you're doing it in live time here, if you wanted to change that, yeah, you just type it into first name Dave.
Yeah, you have to actually type it in and change it to something different.
Okay.
But it will remember them. If you just kind of mess around with doing, like use it like a calculator to start, and then that's what that first discussion board was to get practice in, because every program we write is going to have data stored in variables and outputs. So I like to just get some practice at that right off the bat. And then you can, just build up some strings about those. So
an example of that positional notation.
Oh, okay. So let's do that real quick. Oh, you do not have to do that for the discussion board. You will not need the positional notation. That's just on the homework.
Okay.
I'll send out a message about that. But yes, so let me write another sentence here. Lives in plus town. And just kind of build up 2 sentences to run. Where's that run at?
I think I lost you there. Can't hear you.
Can you hear me now?
Yeah, I can hear you now.
Okay. Yeah, I accidentally muted it. Yeah, I'm going to close out all that other stuff and run this real quick. Just so there's a couple sentences, and it'll be okay to refer to yourself in third person. So if we wanted this in positional notation, that's a, whoops, I forgot to share my screen. Okay, so if we have these sentences, kind of put it together, and you won't have to do this on the discussion board. I'll go make a note about that after class. On discussion board. I'll change that in the instructions afterwards. So you can use regular variables, but it's some sort of encoding scheme. So to do comments, we use the hash symbol. So we can just set up something that means something. So like maybe 2 digits for the date. Then 3 letters for the month.
So we're just making up like a language or names.
And then maybe 3 letters. 3 letters for programmer initials. Yeah, some sort of encoding scheme. It can be really useful if you get used to it, which doesn't take long, but we won't be working with it long enough to get used to it. And then a letter and a number for data type. Letter and number for data type. Does that make sense? So it'll have start with the date. So we'll change name here to something that has the date, which is what? 26 October. Then 3 letters for the initials. CSF wrote it. Then a letter and number for data type. So this is the string, and this is the first one we got to. So that's what the name variable would be. Instead of retyping that everywhere, we hit copy there, and if you hit Control H, you get this defined and replace box. So we can just look for name and replace it with that variable. Just hit replace all. So that switched every place the variable was called name. It's now indicated that it's the first string wrote by Chris on October 26th. You see how it has a lot of information that would be useful on a big team? Or if a computer was writing the code, if we set up a computer to write code for us, we could still dig through and determine information from that variable name.
And what was the like the letter and number for data type? What did you make for that?
I used S1 for the first string.
Okay.
So then age, that's going to be the first integer, right? So like the first integer used here, so that S would change to an I for integer, but it's still written by me on October 26th. So the rest of that encoding scheme is still valid. So I hit Control H, look for age, and change that to an I and replace all those. And then town, that's a string again. So still written on the same date by the same person, but this is the second string, so S2. Then hit Control H and just change those all at once.
And what was the IL? Was that the
I1, so like int 1. I guess I could do 3 letters there.
So the first integer, that's what you had there?
Yeah. So instead of S1, do like STR1 or INT1. But you can just make up an encoding scheme right like that. Maybe what class it is, what homework number, and something that encodes information about who did it and things like that. The point of it is just to be familiar with positional notation. We're not going to do it after week 1, and we put it on. It's on week 1 because there's less programming assignments this week than every other week. So won't have to use it as much, and there'll be small ones. They'll be like store a variable and then print it right back out to the screen. So hopefully it won't be bad working on those. Does that make sense?
Yeah.
Yeah, and it's so much easier to work with a useful name and then hit Control H and change them all at once. And just write up some sort of key for what the variable needs to look like, or what the encoding information holds. Does that seem like enough to get you started just messing around with Python?
Yeah. Mm-hmm. Yep.
Mm-hmm. And for the first couple of days, just use it as a calculator. That introduction board, that's to practice storing the variables and outputs, because we'll use those everywhere. And then do use it like a calculator for a couple of days and see if, just to kind of get used to looking at the screen in idle and maybe seeing what error messages pop up. That's a big thing we're going to look at here, because we can talk about algorithms and go over the proper syntax and what to do right, but it's a lot more important to learn what to do when things go wrong, right? When problems arise, how do we find those problems? And how do we know what to do to fix them? So that's that'll be a big issue in our examples, is we're throwing in errors and then figuring out how to fix them, making sense of all that. Do you have any other questions?
Nope.
Okay, so I guess that we'll kind of wrap it up for tonight. We got through all that review section, which the book spells out really well. I remember I was very happy with those first couple chapters in the book, which I have to remember to go upstairs and grab the 5th edition. I grabbed the wrong one off the shelf. So the book spells that out really well. But a lot of it should have been reviewed from the 120 class. So now that we're through with that, the rest of the semester we'll be writing programs every time. So if there weren't any other questions, I guess that'll be it for this evening. And I will be sitting right by my computer until the time that's on our schedule. So if you have any questions, just send me an email or a text message or something, and we can jump back on Zoom and address those questions. And that's what we'll be doing every time. After we finish the lecture part, there'll still be an hour or so that we'll call lab time, where we won't be on Zoom, but I will be right beside my computer so I can jump back on here with a couple seconds notice and answer and address any questions. But otherwise, I will see you all on Wednesday. Thank you for showing up this evening. I'm going to send an email to your classmates to let them know they need to be coming to the Zoom sessions.
Okay. Yep. Thank you for your time too.
See ya.
Yep. Bye.